Projectile motion. Thanks for watching this video, and don't forget to like, subscribe to the channel and activate the notifications. It's very important to the continuity of this channel. A projectile is any object that, once thrown vertically upwards or thrown upwards at an angle theta to the horizontal, continues in motion, and the only acceleration acting is in the vertical direction, which is acceleration due to gravity, g. Look at the examples of projectile motion. A ball is thrown vertically upwards. A ball is thrown at an angle theta to the horizontal. The movement of falling objects, as discussed in the video about free fall, is a simple type of one-dimensional projectile movement, in which there is no horizontal movement. As free fall has already been studied, the free fall movement will not be studied again. An object is thrown vertically. In the vertical launch, an object is launched vertically up or down without taking into consideration any kind of friction with the air. It is a uniformly accelerated motion in which the acceleration is gravity. Pay attention. After the ball has been released, as the pull of gravity takes effect, the ball slows down, stops at the top of its motion, and then falling back to Earth. The ball is going vertically up and then vertically down to land in the same spot from where it began. As the ball rises upwards, it moves more and more slowly. It decelerates because of the force of gravity. The initial velocity is vertically upwards, so its magnitude is steadily decreased to zero, which marks the maximum height of the path. The velocity then reverses direction, and its magnitude becomes larger with time. It is important to use a sign convention here. We will take upwards as positive and downwards as negative. So the ball's initial velocity is positive, but its acceleration g is negative. The equations of rectilinear motion can be applied to any motion in a straight line with constant acceleration. The vertical motion, up and down, it is motion in a straight line and the acceleration is g. Therefore, all that we should do to analyze this motion is using the formulas from motion in a straight line and the uniform acceleration and rewriting them to reflect the sign convention. Pay attention. Let's see how it works. A ball is thrown vertically upwards with an initial velocity of 15 meters per second. The figure shows when the ball is 5.5 meters above the point of release. Find the maximum height reached by the ball, the time it takes the ball to reach its maximum height, the time when the ball will be at the position shown in figure. Look at the figure. We have to identify the appropriate equation to determine the maximum height. When the ball is at its maximum height, the velocity is zero. So take the third equation. Replace the initial velocity with 15, the gravity with 9.8, the velocity at the maximum height with 0, and perform the calculations. To find the time it takes the ball to reach its maximum height, we take the first equation. Replace the initial velocity with 15, the gravity with 9.8, the velocity at the maximum height with 0, and solve for the time. To find the time when the ball will be at the position shown in figure, we take the second equation because we know the height, initial velocity, and the acceleration of the ball. Solving the quadratic equation, we get two values, as we know the ball will pass through the point twice. A projectile is thrown at an angle to the horizontal. When an object is thrown obliquely near the Earth's surface, it moves along a parabola and subject only the force of gravity that produces the same downward acceleration on all objects. We make the assumption that air resistance has no effect on the object. To illustrate the ideas involved with a projectile thrown at the angle to the horizontal, think of a ball being projected with an initial velocity u at theta degrees to the ground as is illustrated below. Any vector, including the velocity, can be broken down in two components, vectors that have the same directions as the Cartesian axis. So the initial velocity can be broken as the sum of x component and the y component. The magnitude of both vectors can be calculated from the angle that the vector forms with the horizontal through the well-known expressions. Pay attention. The ball moves horizontally and vertically at the same time, and the acceleration acts vertically downwards. There is no acceleration in the horizontal direction, which means that the velocity of the particle in the horizontal direction remains constant. So we can remove the zero subscripts from the horizontal velocity. We can treat the horizontal and vertical motions separately, because the vertical motion has acceleration and the horizontal motion doesn't. We start with the horizontal motion. Because there is no acceleration in the horizontal direction, the horizontal component of the object's velocity remains unchanged from its initial value, and to get the horizontal displacement, we multiply the velocity by the time. The most important in the vertical motion is that the acceleration is constant. So we take the equations above and replace the acceleration with minus g and the initial velocity with y component times the sine of theta. The resultant velocity is the sum of the components. A ball is thrown with an initial velocity of 20 meters per second at an angle of 30 degrees to the horizontal. Calculate the maximum height, the time of flight, the range horizontal distance traveled by the ball, and the velocity at t equals 1.3 seconds. We start by splitting the initial velocity of the ball into the horizontal and vertical components, because whatever equations we are going to use, we will need these quantities. Pay attention. To find the maximum height, we must analyze the equations and look for the one that answers our question in the fastest way. I think this equation does. When the ball is at its maximum height, the vertical component of its velocity is 0. It still has a horizontal component, which is constant. Substitute the values and perform the calculations. The time of flight is the time the ball takes to return to the ground. In this case, the y value will be 0. We must analyze the equations again and look for the one that answers our question in the fastest way. I think this equation does. Substitute the values and solve the quadratic equation. Clearly, t equals 0 is the time when the ball is thrown. So t equals 2.04 is the time when it lands. Therefore, the flight time is 2.04 seconds. The range of the ball is the horizontal distance it travels before landing. We can find the range by using the equation for horizontal displacement and substituting t by 2.04 seconds. To find the velocity at 1.3 seconds, we must find the vertical component at this time first. Take the formula and substitute the values. The vertical component is negative because it is downwards. To get the magnitude of the resultant velocity at this time, use the Pythagoras theorem. To find the direction, we use this equation. Now, look at the figure. A projectile is thrown horizontally. Now we will look at the motion of a projectile that is thrown horizontally from a point above the ground. The equations are the same as we used in the previous example. I know you should be tired to listen me again, so I will not speak from now and then. But do not worry because this example is self-explanatory. Thanks, folks.